Okay, this lesson covers concepts involving parallel lines and properties of quadrilaterals. So another concept that you saw a lot of in geometry class, but it does come back on the ACT. So this is a picture that you've seen a lot of in geometry class, a set of parallel lines cut by a transversal, and they label the different angles. And it was up to you to know the relationships between those angles and the names of those relationships. So first thing I want to review are those relationships, and the first one is vertical angles. Vertical angles are always congruent, and they're kind of head-to-head. So the example I can give you is 2 and 3 are both vertical angles to each other. So we're going to list out the rest of the vertical pairs, and the one that I see right by 2 and 3 are the pairs of 1 and 4. And then if I move down to the next intersection of the transversal, I see 5 and 8 and 6 and 7. And those are the pairs I'm looking for. The next concept were corresponding angles, and they are also congruent angles. The example I can give you is 1 and 5 are corresponding angles. I kind of think of them as being the same house but on different streets. So if 1 and 5 are corresponding, then the other pair that we see right there are 2 and 6. And if I move down to the other side of the street, 3 and 7, and then 4 and 8. Okay, alternate interior angles are also congruent angles. The example I can give you are 3 and 6. They're called alternate interior angles because they're on alternate sides of the transversal. One's on the right, one's on the left, but they're both on the interior of the parallel lines. So 3 and 6 is one pair, and the only other pair in the picture for alternate interior is 4 and 5. Now, there's also something called alternate exterior. So they're still on alternating sides of the transversal, but this time they are on the exterior of the parallel lines. So the example I can give you are 1 and 8. So the other pair of alternate exterior would be 2 and 7. Same side interior, I think our new geometry textbook calls these consecutive interior. They're going to be on the same side of the transversal, but they're both going to be on the inside of the parallel lines. They are no longer congruent. Instead, these angles are supplementary, meaning they add up to 180 degrees. So the example I can give you are the pair 3 and 5, which means that 4 and 6 are the other same side interior, or consecutive interior. There's also consecutive exterior, so they're on the same side of the transversal, but they are on the outside of the parallel lines. So the example I can give you are 1 and 7, and the other pair then would be 2 and 8. Now on the ACT, it's probably not as important that you remember the names of what these pairs are, but it is very important that you remember their relationship. So whether they are congruent to one another or whether they are supplementary to one another. So in our trapezoid, AB is parallel to DC, and they want to know the measure of angle C. Well, if I know that these lines are parallel, then I can come up with a relationship between these two angles. These are same side interior or consecutive interior, and if I flip back to the last thing I worked on, same side interior is supposed to be supplementary. So if this is 80 degrees, his neighbor is going to have to be 100 degrees because they need to add up to 180. Okay, in our figure below, DE, B is on DE, and DE and AC are parallel. Which of the following congruences must hold? That's an ACT way of saying which of the following must be true. So it's got to be one of those relationships, whether it's vertical angles or alternate interior angles or corresponding angles. We'll have to see what happens. So 1 and 2. I can't really think of any of those relationships for 1 and 2. They might be congruent, but I can't tell you for sure. 1 and 4, they're not even on the same transversal, so I'm going to go with no. 2 and 3, again, I can't tell you for sure. I don't have enough information. 2 and 4, I don't know. I'm not sure yet. Ooh, 3 and 4. Look at that. 3 and 4, I can definitely say are congruent because of the alternate interior angles. They are congruent. Okay, this next question says we have a trapezoid and yada yada. Because this is a trapezoid, we know that BC and AD are parallel. So the question is, what's the measure of angle BDC, where the question mark is? One thing I want to point out to you on the ACT, those little moon marks do not mean congruent. I know back in geometry class, sometimes we use those to mean congruent. They do not mean congruent on the ACT. So first thing I notice is if this angle right here is 30 degrees, doesn't that mean that this angle right here has to also be 30 degrees because of alternate interior angles? Now, I'm looking at these three angles put together. 1, 2, 3. Since they form a line, they'd have to add up to 180. So I know the 105 I have to take off, and now I know the 30 that I have to take off. And when I go ahead and subtract those, I am left with 45 degrees, and that's my answer. All right, moving along. In the figure below, M and N are parallel, and we have transversals R and S. Blah, blah, blah. What is the value of angle of x degrees? So, I think we need to fill in some things. If this is 65 degrees, okay, there's a few things that could fill in, but let's talk about the 100. His neighbor right next to him has to add up to 180 because they form a line. So this has to be 80 degrees right here. And I think I'm kind of done. If this is x degrees, doesn't that also mean that this guy is the same size because of vertical angles? So now you can kind of zone in. We've got a triangle right here. And triangles always add up to 180 degrees. So if I go ahead and take away those two base angles, I am left with my leftover guy, which is 35 degrees. Now there are other ways to get that question right. Sometimes you just start filling in numbers until you stumble upon the right answer, but in my opinion that was the fastest way to get there. Also, they'll give you a warning on the ACT that the pictures are not necessarily drawn to scale, but on the ACT they usually are. So if you really are stumped on a question and you're just kind of looking at the picture and it looks like a teeny tiny angle, like this one for instance, he doesn't even look like he could be 80 degrees. So I wouldn't, if you're going to guess, don't guess the one that doesn't even look appropriate. If all you have to go off of is the picture, it's better than nothing. Now that was a pretty easy question, so I hope you don't guess on that one, but just something to think about. The figure below, yada yada, AC is parallel to DF, and BE is congruent to BF. So we've got a little isosceles triangle there. What's the measure of DEB, where the question mark is? Well, we can do this. Since these are congruent pieces, this angle up here has to also match this angle up here. So this is also 35 degrees right here. And I'm looking at these parallel lines, AB and DE, and I'm seeing that these are consecutive interior or same side interior. Now they're definitely not congruent, but they are supplementary, meaning they add up to 180. So 180 minus the 35 is going to give me my leftover 145. And that is my answer for angle DEB. Okay, next problem. This one is a thinker. In our figure, they tell me some things are collinear, and they tell me some right angles are as marked. And the question is, which of the following statements are not justifiable from the given information? So we're looking for which statement is false. This is kind of hard to do. So we're just going to read through them and we're going to put yes, no, or maybe, depending on how we feel. So AB is parallel to EF. Now AB and EF being parallel. I know from the picture you guys think it's parallel. They actually are parallel. If you can give me a reason, you can put yes. If you aren't sure, you can still put a question mark. But the reason they're parallel is if this angle is 90 degrees, and then this angle is 90 degrees, right here, then since the alternate interior angles are congruent, these lines have to be parallel. That's using that postulate in reverse. So this is true, which means it's not the answer we're looking for. DE perpendicular to BE. Let's see. Here's BE, here's DE. Well, yeah, they're perpendicular because they meet at a right angle, and that's the definition of it. ACB is congruent to FCE. So here's ACB, and here's FCE. And I think those are vertical angles, so yes, this is definitely congruent. ABC is similar to EFC. ABC, and then EFC. And the answer is yes, they are similar. If you weren't sure, you could still put a question mark. The reason they are similar is because of something called the angle-angle postulate. If you have two angles in a triangle that are congruent to two angles in another triangle, that proves those triangles to be similar. Not necessarily congruent, but definitely similar. And then CE is congruent to ED. Let's look at that. Here's CE, and here's ED. And while you might think those are congruent, there's no actual information or postulate that we can use with the given information that will prove them congruent. We don't have enough of that information. We need to know something else about an angle or one of the sides. So this is the one that we can't necessarily say is true. That was a thinker. Okay, next problem. In the figure below, transversals R cross both P and Q, and angles A degrees and B degrees are measures, blah, blah, blah. Lines P and Q will cross somewhere to the left. So way over here, these guys are going to eventually intersect. The question is, which of the following statements is true about the relationship for A and B? Now, you got to think about this. If these lines were parallel, the two angles, A and B, would have to add up to 180 degrees because that's same side interior or consecutive interior. So you only have a couple of options. One could be an acute angle like 30 degrees, and that would mean the other guy has to be an obtuse angle. This is if they're parallel again. But the biggest they could be would be 90 degrees. They could both be 90 degrees and still have parallel lines there. Now, the way it's drawn, it looks, and it is, true that A and B are both bigger than 90 degrees. They're both obtuse angles. So think about adding together two numbers that are both obtuse. You know, something bigger than 90 plus something bigger than 90. We're going to get a value. I don't know exactly what it is, but I know it's going to be bigger than 180. And that's the answer that they're looking for. A plus B is greater than 180. It was very fortunate that they drew us a picture in that problem, because that would have been really tough without the picture. Okay, quadrilaterals. A quadrilateral is any closed shape with four sides. And any type of quadrilateral I can draw you is going to add up. The sum of the interior angles will always be 360 degrees. So this guy, they just want to know angle C. We're going to go ahead and add up three angles we do know and take them away from 360. So 360 minus the 27, minus the 99, minus the 118, and I think we're left with 116 degrees. So very easy problem. You just got to know the 360. Okay, let's think about a special quadrilateral known as a rectangle. Now, a rectangle has two diagonals that they can draw in, and the special relationship between those two diagonals is that they are bisectors, meaning they cut each other in half. So that segment's congruent to that segment, and that's true for, whoops, excuse me, this other guy. I want to warn you, if this was not necessarily a rectangle, if this was just any old parallelogram, maybe something that was a little slanted, the pieces would still bisect each other, but they would not necessarily be the same size diagonals. You'd have a long diagonal and a short diagonal, so keep that in mind. Now, if I extend this to a special type of quadrilateral called a square, now that, or a rhombus, now their diagonals are perpendicular bisectors. So they cut each other in half, and for a square they're all the same size, but they're also perpendicular, meaning they form a right angle in the middle. Now be careful on a rhombus. You see how it's slanted, so there's one long and one short? That means that this diagonal is cut in half, and so is this diagonal. However, he's a different size diagonal, so we got to mark him a little differently. But what I do know is for sure it's a right angle in the middle there. So anytime I have a problem that involves the diagonals of a rectangle or a square or a rhombus, it's very likely going to involve maybe some Pythagorean theorem or some sort of bisection. Now when you have a kite, the diagonals are perpendicular to each other. That is true. And this short diagonal is cut in half, but I'm sure you've noticed that the long diagonal is not necessarily cut in half. So you can't label those as such. So this problem is actually really tricky. And ironically, it's tricky because they gave you a picture that's a little misleading. So we have a rectangle, ABCD, with diagonals AC and BD intersecting at point E in the middle. So our rectangle is a square This rectangle is a square if and only if triangle ABE, I'm going to go ahead and color him in, is congruent to which of the following triangles? Now, the way it's drawn, he just looks like any old rectangle. He does not look like a square. So my thought is, if you're a good artist, maybe the next step would be to draw this guy looking more like a square, and maybe the answer would be obvious to you. Now, I'm a terrible artist, so I'm not going to bother doing that. But the way I'm looking at it now is he's definitely a rectangle. He does not look like a square. But what I can tell is angle DEC is already congruent to him, even in a rectangle, not necessarily a square. So that one's not very helpful. Let's look at our choices. ACD. Where is ACD? ACD is this big right triangle here. Well, even if this was a square, I don't think this huge chunk would be equal to that blue guy, so we're going to cross him off. ADE. That'd be this guy right here. Now, I know he doesn't look congruent the way it's drawn, but think about it if this was a square. I'm going to hold off on that one. Okay, BAE. Well, that's himself, so that wouldn't be very helpful. BDC would be another right triangle. It's a huge chunk of the rectangle, so that wouldn't be very helpful in determining if it's a square. And then CDE, it is congruent to ABE. However, that's true for a rectangle, not necessarily a square. So while that is true, it might not necessarily help us to determine if it's a square. This is actually the correct answer. If this adjacent triangle is congruent, then this forces this guy to be a square. And if you don't believe me, go back to a picture of a square. Notice how all the triangles are the same size. That's what makes that a square. Alright, in rhombus ABCD shown below, the diagonal for AC is 8 inches and BD is 6 inches. Now remember, the diagonals of a rhombus perpendicularly bisect each other. So the AC is 8 inches long. Since he's bisected, they're both going to be 4 inches. And then for BD, since the whole thing is 6 inches, they're both going to be 3s. I'm going to go ahead and draw in my right angle symbol. The question is, what's the perimeter of your rhombus? I need to know that guy. And once I know the side, since this is a rhombus, all the sides are the same. Well, I'm seeing a Pythagorean theorem problem. 3 squared plus 4 squared equals x squared. It's a special right triangle. Turns out all these sides are 5. Now don't stop there. The answer is not 5. They wanted perimeter. So the perimeter of this shape is 5 plus 5 plus 5 plus 5, or 20 inches. I guarantee you on an ACT test, the very first answer choice would be 5. And obviously that's wrong because you did not answer their question. Alright, our last example is a rectangle. And it says we've got this lovely diagonal cutting through, which is 13. And BC is 5 inches. What's the area of a rectangle? Well, think about what you need for area of a rectangle. Area of a rectangle is length times width. We need to know how long this rectangle is. Well, I do know that rectangles have right angles on the corners. So I'm thinking we have a Pythagorean theorem problem. But this time, I don't know one of the legs, and I do know the hypotenuse. So let's see, that's 169 minus 25. So that's, whoops, excuse me, that is 144, so 12. Okay, don't stop there. That's not the right answer yet. The area of the rectangle is length times width, or 5 times 12, which gives us 60 inches squared. Very good. It's a tough lesson. Keep these notes handy when you do your practices, because there's a lot of similar problems that will show up on your practices.